Welcome to lesson 25. We're going to add, subtract, multiply some radical terms. So last time in lesson 24 we were basically we would have one radical and we would try to simplify it. In this lesson we're going to have like two or more radical terms, and the question is, how do we combine them and then maybe simplify? But first, how do you combine these two things? Now for adding and subtracting, which is what I'll do first, we'll do multiplying later, but for adding and subtracting, I say it right here, it's a like terms thing. So if you look at this first example, 3 root 2 plus 4 root 2, think of if you had this, 3x plus 4x. You would know what to do with that. We've done that plenty of times, right? If you have 3x and 4x, you would say, like terms. That's 3 x's plus 4 x's. That gets me 7 x's, right? It's all like terms. Well, oops. It's also like terms here. I'll say we got, but we got 3 times not an x but a root 2 plus 4 times not an x but a root 2. And so what we get is 7 times not an x but a root 2. Okay, so it's just like adding like terms. So the radicals are going to be kind of like taking the places of x's in a way in terms of how we apply this rule. So you always want to relate things to what you know, right? I know this, you know this. 3x plus 4x is 7x. Happy with that. Well, what we're trying to say today is that this is like that. This is 3 somethings plus 4 of the same thing. I got 3 of them, I got 4 of them, I got 7 of them. Okay, that's the whole idea of like terms. Now let's come down to, let's come down to this one actually right here. So root 3 plus root 3. Again, you want to think of this almost as though you had an x plus an x, right? If you had an x plus an x, you'd know what to do. You'd say, I got one of them, and I got another one, so I got 2 of them. I got 2x. So that's what you're thinking of. But this is different, of course. This is not an x, it's a root 3. This is not an x, but it's a root 3. But it's the same kind of idea that you've basically got one of these patterns and you're adding another one to it, and so what you've got is 2 square roots of 3. Just like that, okay? Just like terms. If you wanted to think about this a little bit more deeply, and this is optional, but just kind of go like this. Consider, if I had just 3 plus 3, wouldn't I just add them up and get 6? I sure would. So how come I can't go like this? Root 3 plus, root 3, just add them up like this. No, you cannot do that. And to prove it to yourself, just get your calculator out, take the square root of 6, and then take the square root of 3 and add it to itself and see if you get the same thing, and you will not. It doesn't work that way. It doesn't work. So with 3 plus 3 equals 6, fine. With 3 plus square root of 3, if you really wanted to do it like term, excuse me, I didn't want to talk about that. I wanted to talk about this one again. If you wanted to do it the same way we've been doing it, where you think of the 3 as sort of a 1 times 3 plus a 1 times 3, you've got like terms because it's 1 times a thing plus 1 times the same thing. So I got 2 times, notice you get 6 in the end. Okay, now don't worry about that. It's not going to be on the test or anything like that. It's just, I throw that idea out there just because some of you are going to be curious and want to go, But as long as you get this like terms idea, that's the main thing. You want to recognize these things the same way you would play with like terms, with x's and y's and things. So let's come back up and look at this example now. Root 2 plus root 3. Question, are they like terms? Well, that's a root 2 and that's a root 3. They're different. They're not the same kind of terms. They're not the same kind of pattern. So leave it alone is what you do here. Just leave it alone. And maybe as a sort of a reference, if you had an x plus a y, you would leave it alone, right? Because they're not like terms. One thing's an X, the other thing's a Y. They're not the same. It's apples and oranges. It's not apples and apples. You don't do anything with it. So same thing here. You don't do anything with it. There's nothing to do. They're not like terms. So you can only combine like terms. But if they are like terms, you should combine them. So let's look at this one now. Down here, you got a root 5, take away 2 root 5. Do you see like terms there? Well, that's a root 5 pattern, and that's a root 5 pattern. So yes, we do have like terms. By default, this is 1 root 5 minus 2 root 5. And you can think of this as a 1x minus a 2x, right? Just instead of root 5, I'm putting an x there instead. It's equivalent. It's completely equivalent. The point is I got 1 times a pattern, 2 times a pattern, 1 times a pattern, 2 times a pattern. It doesn't matter what the pattern is. It doesn't matter what it is. If you got 1 of them and you take away 2 of them, you've got negative 1 of them, right? Negative 1x, or just negative x. So here it's the same thing. 1 minus 2 is negative 1 root 5, or just negative root 5. Okay. Like terms means take the coefficients. Coefficients are the numbers in front, the multipliers. Take the coefficients and combine those by adding or subtracting. And then the pattern schleps along, so to speak. It follows with you. So 1 minus 2 is a negative 1, and then schlep the root 5 with you. So you could write negative 1 root 5, or you could just write negative root 5. So, okay, like terms, all about the like terms. Come down here to this example. Root 8 plus root 18. Well, they're not like terms, or at least they don't look like terms. That's an 8, that's an 18. That's not going to work, right? That's a radical 8, that's a radical 18. But you have to go like this. First you say harumph. I said harumph because this is going to be more work. Harumph, right? That's what you say when it's going to be more work. Harumph. We need to simplify these first. So remember from the past lesson, let's try to keep that separate. Remember from the last, but that's what the whole last lesson was about, was just simplifying radicals. You have a root 8. Well, we can simplify that. Remember there's a thing called the tree method. You could take the 8, you can break it up into a 2 times 4. The 4 you can break up into a 2 times a 2, right? And then you do the old, hey, I got a pair of 2's. That'll release a 2 to the front, and I'll still have a 2 on the inside. So really, radical 8 is the same thing as 2 radical 2, right? If you're not remembering this, you should just go back to the previous lesson and have a quick speed through. Then we've got this plus. Then we've got this radical 18. Let's play with that one first, tree method. You could tree it however you want. You can go 2 times 9, you can go 3 times 6. I'm going to go 3 times 6 just because. And then the 6 I can break up further as a 3 times 2. So this is what we're looking at. We're looking at a 3 times a 3 times a 2. Remember, that's called the prime factorization of the 18 because we broke it down into all its little primes, prime factors. 3 times 3 times 2. I got a pair of 3's. And if you got a pair of 3's, that'll release a 3 to the front. Still got the 2 inside, so you leave the 2 inside. So we simplify first. Then we look at it and we go, hey, we do have like terms after all. It's just that they were disguised. So having simplified root 8 and simplified root 18, we look at this and we say, I got 2 thingy-wingies plus 3 thingy-wingies gives me 5 thingy-wingies. Of course, you don't have to say thingy-wingies, but that's the idea. It's like I got 2 times a pattern plus 3 times the identical pattern. So I got 5 times the pattern. Just like 2x plus 3x equals 5x. 2 root 2 plus 3 root 2 equals 5 root 2. Okay, this one is the big one. I'm going to save till last. Because it turns out this one actually involves a little bit of combination moves. Yeah, we'll save that till last. Let's go learn about multiplying first. We'll come back to that one, I promise. So skipping to page 2, start multiplying. Now here's the key phrase for multiplying. Insides, outsides separately. So adding or subtracting was like terms. That's what we were doing before. That's what you do when you're adding or subtracting. When you're multiply, like terms got nothing to do with it. You actually just multiply what's inside the radicals, and separately you multiply what's outside the radicals. Here's what that looks like. So root 3 times root 5. Well, the 3's inside, the 5's inside. 3 times 5 is 15, so the 15's inside. You get root 15. So I love multiplying because you just do it. That's the nice thing about multiplying. Just do it. Adding or subtracting, well, you got to fuss about the like terms. But multiplying, dividing, you just do it. And if you're having trouble believing me, you can actually get out your calculator, take the root of 3, and then take the root of 5, and then multiply those together, and compare to the root of 15, and you'll say, oh, they really are the same. They really are the same. This really does work. This example over here, notice I got outside, inside, outside, inside. The 2 and the 3 are both outside the radical. Multiply those together. And then separately, the 3 and the 7 are inside the radical, so you multiply them inside the radical, and you get 6 radical 21. And that's basically the name of that game. Multiply outsides and insides separately. Now sometimes you'll get a number inside that you can simplify, like, can I simplify root 21? You should always take a look at it. We really can't. If you were to tree that out, all you're going to get is 3 times 7. You don't get a pair of anythings. So the 27, the root 21 is not going to simplify any further. Okay, let's come over to this one. Oh, can you say distribute? Yeah, we can do all kinds of distributing and foiling and all that same kind of stuff that we used to do before. So we recognize a distributing thing because I have something up against parentheses, and the parentheses has 2 terms in it. So, okay, here we go, not a foiling. Here we go, a distributing. So you multiply the square root of 3 times the 2. Well, the 2 is outside, the square root of 3 is inside. You get 2 square roots of 3. The insides and the outsides don't mush when you're multiplying. Now, when I multiply the root 3 times the root 5, well, they're both a pair of insides, right? It's going to be a root 15. Notice the minus is still there. So I got 2 root 3 minus root 15. And that's it. These are not like terms. The root 15 is not going to, you can only tree a 15 into a 3 times 5. You're not going to get a pair of anything. So that's it. You're done. That's it. That's all you can do. Now this one, I'm going to put a flag on it or a star on it because this comes up a lot. Root 3 times root 3. You could say, well, by the rule that we're using, it would be multiply the 3's together. So you'd have the root 9. But hey, root 9, that's just 3. And so I've got a little thing for you to, you could take a shortcut on these things. And call this a tip. Tip. If you have a square root of a thing, in this case it was a 3, and then you multiply it by the square root of the same thing, exactly the same thing, in this case a 3 again, then you get just the thing. I don't know, weird phrases like this, they really help me anchor stuff for some reason. Hopefully it would work for you too, and if it doesn't, well, make up your own phrase. But anyway, this works for me. It's like, I got the root of a thing times the root of the same thing is going to be just the thing. The root of a 3 times the root of a 3 is going to be just the 3. That's what I'm saying. The root of a 3 times the root of a 3 is going to be just the 3. And it's going to work for anything else in the world. The root of a 5 times the root of a 5 is just the 5. The root of an x times the root of an x is just the x. And so on and so on and so on. The root of a 5x times the root of a 5x is going to be just the 5x. So whenever you're repeating the same thing, it's always going to just come out to, it's like the square roots go away. They go away because when you multiply by yourself, that's like a squaring. Squaring makes a square root go away. So let me erase that mess. Don't really want to mess up our stuff here. What would you do now? What did you do? This is supposed to be the easy way, right? What are you doing to me now? Whoa. I have to learn this whole world of touchscreen still. So anyway, root 3 times root 3 is just 3. Okay, that'll come up a lot. It comes up more often than you'd imagine. So like it's going to come up right here in this next problem where we have some more distributing to do. So you multiply the root 3 times 1. Anything times 1 is itself, right? And then we have to multiply root 3 times a negative root 3. So I'm going to get a negative. And remember what we were just saying. Root 3 times root 3 is just 3. Which saves you a little bit of time from going through the whole, well, that's root 9, but wait, that's a 3. You know, it saves you, if it saves you a second times 20 problems, it's like, it's worth it. Over here, another distribute type thing. This one's a little more involved. So you want to multiply 2 root 2 times 2. Well, outside is a 2 times a 2, and then inside is another 2. So outside, I'm using O for outside there, is 2 times 2 is 4, and then inside is radical 2. So you get 4 radical 2 when you multiply these first things together here. Let's look at multiplying this together. Well, again, you do the outsides and the insides separately. First, notice we get a plus. So the 2 times a 3 is giving me a 6. And then I have a root 2 times a root 2 is a 2. Now this is a big string of multiplication, right? It's 2 times a root 2 times a 3 times a root 2. You can arrange multiplication in any order that you please. Right? So I'll just scramble this up a little bit. So notice the 2 times the 3 is giving us a 6, and the root 2 times the root 2 is giving us the 2, and so it really is a 6 times 2. So, sometimes if you're, if you see me write like a 6 times 2 and you're not quite sure where it comes from, what you can do is you just break things up into their little itty-bitty pieces and then put them back together one at a time, kind of like taking a Lego thing and smashing it into every single little piece. Well, don't smash it, you might break it, but, break it up into every single little piece and then put it back together one piece at a time. Where are we? I've got a 4 radical 2 here. Nothing you can do with that. 6 times 2 is 12. That's all you can do with that. These are not like terms. It's pretty much done, right? Although I might write more conventional, if you will. More conventional is to put the number first, radical term second. Kind of like, when you have x squareds and x cubes and stuff, you usually put the x cubed first and then the x squared. It's just a convention, right? It's called standard form. This is similar. We would actually put the 12 first plus the 4 radical 2. That would be more conventional. In this class, I'm going to accept either one because they are the same, of course. But just so you know, a lot of times you're going to see it rearranged like this. Might not be a bad habit to get into. Actually, while I'm looking at this, let's say you were working in a textbook or something, and you're looking up the answer in the back. You might not even see this answer. You might see the answer written this way. Do you remember how to undistribute? Both of these terms have 4s in them. So sometimes people would undistribute the 4 and write it this way, which is cool, very cool. If you write it that way, you might make me so happy I give you a bonus point. But if you like, you can stop here. It's just good to be aware of how this is really the same thing as this, which is really the same thing as this, and so on. You want to start developing an eye for, things that look different at first sight, but really they're the same thing, right? That's half the battle, I think, in a math class. Okay, so we did the add subtract, which is like terms. We did the multiply, which is insides and outsides separately, with that little shortcut. Root 2 times root 2 is 2, and so on. Now some combination moves. This is where the foiling is going to start happening. So I only got 2 of these FOIL problems. And you kind of know what to do, right? You recognize, oh, yeah, that's like foiling, right? So you do the first, the outers, the inners, the last, and so on, right? So let's look at the 3 times the 2 and say 6. There. That was fun. What's next? Whoops. What's next? What the? Hey, you. Okay, we're gonna get this figured out. 3 times 2 is 6. Right. Okay. So here we go. Now you have to go the 3 times the root 5. So that's basically a 3 on the outside, root 5 on the inside. That's all you can say there. Okay, I did the outers. Now I should do the inners. Well, that's a 2 on the, well, it's negative for one thing. Notice that, right? Negative times positive is negative. It's a 2 on the outside. It's a root 5 on the inside. So I'm just going to leave that there for now. And then don't forget, you got to do the last terms. Minus times plus is minus. And then this is one of those root 5 times root 5 is just 5 type situations. You could say it's the root of 25, right? 5 times 5 is 25, but the root of 25 simplifies to just 5. So there, we went and we FOILed. Now we've got a big old addition subtraction thing going on here, and you want to say, oh, that's like terms. Notice the 6 and the -5 are both numbers or constants, so those are like terms, so you can combine those, you add them together. A 6 and a -5 is just a 1. And then you look at these two terms and you say, by golly, those are like terms also. I got 3 times this pattern and then -2 times the same pattern. Like terms. Let's write that down. Like terms. So you can combine them. 3 of them minus 2 of them will leave you with 1 of them. So it's just -1 root 5. You can write 1 root 5, or you can just write root 5. Cool. Okay, we got 2 problems to go. This one and the one that we forgot on the first page, or didn't forget, we skipped on the first page. This is another FOIL type thing, and actually I'd invite you to pause the video and try this one yourself. Back so soon? Okay. Well, FOILage. First terms, 1 times 1 is 1. I love being able to erase. This is great. 1 times this, right? Notice it's a negative. It's a positive times a negative is a negative. Outside the radical, we have 1 times 2 is 2, and inside the radical is just, well, it's just radical 3 is what it is. Just like, 1 times a -2x would be a -2x, right? That's kind of what we're getting here. 1 times a -2 root 3 is a -2 root 3. Sorry for squishing that in. Okay, it's the same pattern, same idea. Like I say, the key always is to relate things to what you already know. Otherwise, you're just trying to memorize all kinds of stuff, and that's too hard. So anyway, now we got to do the inner terms. So that's anything times 1 is itself, right? So 4 root 3 times 1 is going to be 4 root 3, and notice it's positive. And then we do the last terms. Positive times negative is negative. 4 times 2 on the outside is 8. Root 3 times root 3 is just 3. Okay, so again, I'm kind of multiplying this. Again, when you've got a string of multiplication, this is all multiplication. 4 times the root 3 times the 2 times the root 3. You can arrange the multiplication in any order that you like, right? And so this is where I'm getting the 8, and then this is where I'm getting the 3. So it's a 24 is what it is. So I got a 1. Let's combine these two together. They're like terms, right? Root 3 and root 3 they're both the same. So I got a -2 plus a 4. It's going to give me a +2 radical 3. And then don't forget I got this -24 at the end. And so now I should combine the 1 minus the 24. And here's what we're looking at. -23 plus 2 roots of 3. Cool. Now, we have the one problem from the first page that we didn't do. It's right back here, right? I'm going to actually do it at the end here. I'm going to copy it because we've got plenty of space back here. So let's copy that problem back. Okay, it was this. It was x, so new problem. X radical 27x minus radical 75 x cubed. Okay. Now this goes back to the first thing we were doing, which was, hey, you want to add and subtract stuff? You need like terms. You look at this at first and you say, those terms don't look the same. But you should notice that they're not simplified, like especially if you have an x cubed. You shouldn't have any exponents inside of a square root, because that means it can be simplified. But also 75, that seems like a big enough number. We should be able to reduce it, and even the 27. So we have to simplify first. This is if you want to be complete, you'd have to say harumph. Simplify first, because these are always the ones that are like, oh, this is going to take longer. Not much longer, but it's going to take longer. Now, I'm going to split apart. Split up the Legos. I think I have to capitalize Legos or something. Split up the Legos. So this term is going to be x times a root 27 times a root x. Remember when we used to have, if I could, maybe I could cover this up somehow. If I could cover up that for a minute. Remember how we used to do radical 27x? I said you split the number from the variables up. Do the 27 separately from the x. Okay, that's the convention I'm following here, except that we also have this x in front. Okay, so the 27 tree method, that's a 3 times a 9. The 9 is a 3 times a 3. So notice we get a pair of 3's, which is going to give me a 3 outside, and I'll be left with this 3 inside. Okay, so I have this x in front. This thing in the middle is reducing to 3 radical 3, and then I have this root x at the back. And now, put the Legos back together. Remultiply these things, outsides and insides separately. I get a 3 times an x outside, that's a 3x. I got a 3 times an x both inside. So actually, that's my simplified version of the first term. It's 3x times the square root of 3x. Want to try that one yourself? Another pausing opportunity for you. Well, what I would do is, and let's just put the minus there so we don't forget. There's a big minus, right? This is going to be, let's see, if I split this up, I would split it up as a root 75 times a root of x cubed. And the 75, we got to do the tree method on this thing. Let's see now here. You know what that would be? Let's see. What goes into 75? Well, it's 3/4, right? Quarters meaning 25-cent coins. It's 3/4, so it's 3 times 25. And then the 25 is a 5 times 5, of course. Lo and behold, we got a pair of 5s. So there's going to be a 5 released to the front, and then we still got the 3 inside. Don't lose it. So that's how the root 75 part simplifies, is to a 5 root 3. Now remember how we did x cubes? One way we did them was we said, hey, hedgerow method. The x cubed is going to break up into an x times x times x. You don't really have to tree it out. You can just hedgerow it. But again, you get a pair of x's that's going to release an x to the front. And then you'll still have this x left inside. So you've got a 5 radical 3 times an x radical x. We're going to put the Legos back together now. Multiplying outside, I have a 5 times an x. Multiplying inside, I have a 3 times an x. So I have a 3 times an x inside. Okay. Now, let's look at where we ended up here. 3, oopsie. Okay, 3 times minus 5 times. Notice the part that I've kind of underlined there. Those are repeating patterns. Repeating patterns tells you probably have like terms. As long as you have just a number in front or even a 1 in front. You wouldn't, if you threw a y in front, that would mess it all up. But as long as you got numbers in front. So you got repeating patterns. So you can just go like this. 3 take away 5 is a -2. And put the pattern there. It turns out that is our answer to that one. -2x times the root 3x. The x root 3x is like a, well, that's what makes it like terms. 3 of them minus 5 of them means I have -2 of them. And you put the of them back in there. So it's -2x root 3x. Now, that one's maybe a little intense. It sure looks like I used a lot of ink, so to speak, right? The best thing to do, I mean, either you're getting it right away and you're happy, in which case, see you later. But if you're looking at this and you're still kind of chewing on it, going, I think I see, or what? Then what you want to do is you want to kind of chew on this for a little bit. See, make sure you can follow all these various steps that I did. Make sure they all make sense so that you yourself might have the idea of doing such steps in the future. And what you do is you then let about 2 or 3 minutes go by, and then go back to page 1 and try this problem again. Remember, this is the very same problem from page 1 that we skipped on page 1. Just try it yourself. Try it cold. See how far you can get. And when you get stuck, Then you look back here for a reminder of what to do, and this is the best way to burn stuff in. It's when the brain is trying and it's not quite getting it because the connection is a little weak, and then you remember and it puts another pulse right down the very connection you were trying to remember, and that's what makes the connection stronger. This is science. This is not just me talking. This is science. So this is the best way to learn stuff, is to kind of, you struggle with it, and then you get to a point where you're almost ready to try it yourself, but then you wait just a couple minutes. Don't watch TV, please. Don't be checking your text. That'll erase it. That's science too. That will erase it. Just go right back and just try it again. Okay, well, I think I'm talking enough. Let's stop here. We got more videos to do, don't we? How do you end this thing?